it's like a string, it's null terminated and things like that. But in general, what it does is it will cast. So it knows that if you declare an unsigned int, it'll take so much space, that sort of thing. But when you start talking about strings, the size will be defined as, say, 200 bytes. It's called a static buffer. It means it takes up so much space in memory, period. If you overwrite it, you overwrite variables, you overwrite heap, you overwrite stack, you overwrite all kinds of fun things. So let's say this first part of the stack, each of those different colors is a different thing in memory, all right? And very basically, this is where whatever this is used to be. And we overwrote it. So if that's used by a function, that means we can alter the way the function works. We can force it to do something that it wasn't going to do that we're interested in doing. And then obviously, you can also overlay P. Either of these and any number of other options will result in foreign code. So. Each address can only have one value stored at it. So if we overwrite an address at the value stored in an address at a pointer, then that value will change. The old value will be gone. This is, you know, when you see program crashes in C programs, it is often this. It is often crashing because it's really hard to keep track of what's actually happening in memory. There aren't good tools for viewing step by step, you know, what the memory looks like and colorizing it, you know, things like this. With new GUI stuff, that would be incredibly useful, but it's not really out there. Here's the code I'm going to be using. Yay, code. This is just making sure we have an argument. And then it calls the function vulnerable. Vulnerable is defined here. We define a static buffer. And then we use an sprintf. The reason we're using an sprintf is because we can combine nice, good old buffer overflow and format strings. Yeah. In front of a buff, because I'm copying to the address, to the actual pointer to, I don't know. Yeah, well, the pointer would be to the first address to buff 0, so that should be fine. So right here, what we're doing is Perl is really helpful for sticking shit into a program because you can print hex. So I'm printing 1,000 A's. Print A times 1,000. 4.1 is the ASCII code in hex for an A. So if I overwrote those with capital B's, that would be 0x42424242. What this means is that there was a jump to a point that I overwrote, or you know, any number of potentialities. Since I statically defined that buffer, I probably overwrite heap, so I could have overwritten you know, a function pointer or something along those lines. But we'll take a look at what actually happened in a second. So now that we control that jump point, we can overwrite that with the address of our shellcode. I'm storing it in an environment variable. The reason is anytime you launch an executable, Linux x86, blah, 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 you inherit the environment from the parent, which makes it really convenient because since screen is the parent of the process I'm launching, I can keep the same environment time after time, so I don't have to worry about if I log in from somewhere different, this code isn't going to work right because I don't use an op sled, just for accuracy's sake. Environment variables can be found in the heap near the EBP pointer. We'll take a little look at that later for actual seeing where that is and how to look at it. x86 is little endian. Endianness, there's another entire class of exploits, what's called a sort of, they're flaws where the endianness, which means how it's stored in memory, either backwards or forwards. So it's by word. So DEAD would be AD and then DE. The bytes, which are 2 hex digits, are together, but well, each byte is reversed in the word, and a word is 4 bytes in an x86 system. So, or well, like I said, yeah, Linux. And you overwrite that with a function pointer. So what I'm doing here, I'm printing these hex characters, which is Aleph 1's code from smashing the stack for fun and profit to a temporary file, and then I'm running this line, which is actually redundant. I could have removed this entire section here and just moved this back, but I think I actually did that on the system, to cat that into an environment variable, and then I run my GDB string I've prepared here. So that's when we jump into GDB. You usually want to put that in the environment before you launch GDB, so that any processes launched by GDB will have it in the environment. All right, so this, for instance, let's see here. Let's see what we got. Sure, yeah. All right, so the actual line I use here just run A times 5,000, and we end up with segfault here. The way you would actually do this without using these command files, what you see, these last 2 lines, run perl-e, that's what you would type directly into GDB. So you would type GDB, name the executable, and then you would type that line. For those of you who are sort of Unixy, these backticks, anything inside of backticks will be executed, and then whatever was returned by the program will be inside those backticks. You can think of those being replaced. So that will perl-e runs from whatever's on the line rather than what's in a file. That doesn't mean you can't put a file in your home directory and just do tilde/ and then your Perl file or whatever you want to do. So let's okay. This is real straightforward. Basically, I wrote enough A's to override my buffer, and I jumped to a shell here. When you actually do this, since you're doing a jump out of the code, you end up with a sig trap. So don't freak out when you see that. Don't think, oh crap, and Control-C and start over. You're good. You're there. So let me show you what that line looks like. All right, so first off, we're doing the shellcode thing again. This is the exact same thing as last time, prepping the environment the same way. We don't actually have to do this a second time because it's going to stay in the environment. So if we were to do it inside of GDB and then exit GDB, it would not be in the environment because GDB is not the parent of our bash shell. Bash shell is parent of GDB. So we stick it in GDB in the bash shell, and it will be there for GDB every time we launch it from that shell. And then here we see actually the resolution's high, the size is high enough I wasn't able to see this, but I printed this 4.1 here in this one just to show that it said segfault at 4.1 FF F313. When you see that 4.1, 4.1, 4.1, the most intuitive way to start actually exploiting it is to start deleting A's one by one or by in groups. The correct way to do it is to look in memory and find what your offset is, find what you're overwriting, figure out why it ends up in the IP. You don't have to. You won't learn much, but you can do it sort of ghetto style and just start deleting stuff and start throwing B's and C's and D's and stuff in there, and you will see the different values show up in the point that you segfault at. So that was just an example line. This is the actual BF-FF-F351 is the address of egg in our environment variables. And we jump to that address, and we get a shell. Format strings. Printf is a function meant to make text pretty for the console. This string right here will print hello, a space, and that percent, unless it's a double percent, will get read as something special is going on here. So %s, and then it'll print this, Sam, instead of that %s. So what you'll end up with the line is, hello, Sam. Here we define a buffer, a character array, and we stick Sam in there. And then we call the same thing with the name of the character array instead of putting it in the quotes. Doesn't care, sees it as a null terminated string, and it uses it. There's actually something interesting for those of you. Since a string is null terminated, if you can overwrite the null termination at the end of the string, it will continue until it sees another null. And that is a trick you can use sometimes to, when you have limited options for trashing memory, you end up finding little things that let you get away with stuff. And normally, the programmer supplies format strings. User supplies input that is inserted into the string by the programmer. What we're looking for is when this happens. The 08 specifies that we're printing 8 hex digits, because the X stands for a hex digit. And we're printing the address that buff is stored at. Wrong way to do it is printf buff. The reason is, if we have a %s in buff, then it will print whatever string it thinks is pointed to by printf. Whatever. I should clarify that a bit. Printf, when it enters, has its own little like stack, is the best way to think of it for its variables. And when it tries to print %s, for instance, it will go to whatever's next in the stack. But since we didn't enter printf using argv, which allows you to pass multiple arguments, the next thing on the stack could be anything. And eventually, it will be actually the format string itself. So, take advantage of this. %s prints a string. Signedness and endianness are the two things you need to consider when you're talking about intuitively changing C code into what it looks like in memory. And also a ton of crap about how it actually stores memory. So an unsigned decimal integer can only count up, and it can count up to about, what, like 4 billion or something crazy like that. It is literally 4 bytes, or no, yeah, well, I'm not going to try to figure it all out. 8 hex digits is 4 bytes is 1 word. It's 86 Linux. That's, for instance, a